For 4A, they're asking us to find the average speed of water molecules in a vapor that is produced when it boils. Um, so, the first thing to spot is that we're looking for the average speed of water molecules. So we're actually looking at the speed of the individual particles. Okay, so it's the speed of a particle. And the reason it's average is because the different particles all have a range of speeds that they travel at. So what we do is we take the average and we say that's the average speed of the molecules overall. So everything that we do needs to be for one particle. Okay, and that's really important that you spot that. Okay, so let's see what letters we have first of all. We have a mass of water, and then we have a temperature in degrees Celsius. We've got a power of 1.6 times 10 to the 3 watts. We've got the molar mass, capital M, which is 18 grams. So 1.8 times 10 to the minus 2. And then we're trying to find V. So the way we go about this is by putting the kinetic energy of a substance equal to half mv squared. And V is the average speed. Okay. So KB is a constant, Boltzmann's constant, and that's 1.38 times 10 to the minus 23. And so now we have almost all the symbols that we need. So we're going to cross out the 2's, and I'm going to rearrange for V. So V squared equals 3 kBt in Kelvin divided by the mass of one particle. Now we know that 1 mole of particles is 1.8 times 10 to the minus 2. And we know that according to Avogadro's constant, there are this many particles in 1 mole. So if I divide the mass that we've got of that many particles, we can work out how much mass we actually have for 1 particle. And that's 2.99 times 10 to the minus 26 kilograms. Okay, so now we put in the numbers. So what we can do is we can actually say, therefore, V equals the root of 3 kBt over m, which is this number. And we get a value for V of approximately 720 meters per second. Now, for the kinetic model of an ideal gas, there are a large number of assumptions, and you just need to state one. So there's actually 6 that you could have in no particular order. The first one could be particles are considered as points, they don't have dimensions. You could have said there's no forces between the particles, there's no intermolecular forces. You could have said the volume of a particle is negligible compared to the volume of its gas. You could have said the collisions between particles are elastic. The time between particle collisions is far greater than the time of a collision. Or you could have said there's no intermolecular potential energy between particles. So the one that is often written, and the one I'm going to write, is the collisions between particles are elastic. So there's no energy loss to the surroundings. 4C is asking for the specific latent heat of vaporization, which is capital L. So the equation is energy equals mass of the substance multiplied by the specific latent heat of vaporization. You could put a little V there if you want. Fusion is for melting or freezing, and then V is for evaporation or condensing. So we're asking for L and a unit. So it doesn't always matter if you put a unit for your answer, but for this one it does. So I would be expecting you not to gain the answer mark if you don't put the correct unit. Okay, so we started off with an initial mass of water of 1 kilogram. And then we had a final mass, it says here, of 0.86. Sorry. Bear with me. I'm just going to pause this whilst I sort the pen out. Right, so we can work out how much mass has vaporized. So the energy, vaporized. So the vaporized mass, in other words, the energy that has gone into vaporizing the mass, has caused 1 minus 0.86 kilograms, 0.14 kilograms, to change phase. Okay, so we have energy is power times time, and then divide that by the mass that is vaporized, and we get the latent heat of vaporization. So all I've done here is I've said energy is power times time. Okay, and we know that the power was, let me just look it up. Right, I've just jumped up to 4A. The power was 1.6 kilowatts. So we've got 1600 watts, and it's going for 200 seconds. And then divide that by 0.14, and the specific latent heat comes out as 2.28 times 10 to the 6, and it's energy over mass, so it's joules per kilogram. So for 4D, it's asking you to understand and explain why, when there is a change of phase of substance, the temperature remains constant. And that is because all of the energy that's being inputted is being used to increase the potential energy of the particles. In other words, to break the intermolecular bonds. So I'm just going to pause the video and write that now. Like so. For 4E, we've got some cold pasta that is being added to boiling water. So essentially what we've got is, if we did like a temperature scale, we've got 100, and this is in degrees Celsius. We've got minus 10 here. So we've got the pasta at minus 10, the water at 100, and as the pasta is placed into the water, the pasta is going to cook through and warm up. But because we've placed something very cold in the hot water, the water is going to cool down and it's going to settle at a final temperature. And we call that the equilibrium temperature. So, in other words, the energy loss in the water is going to go into the energy gain of the pasta. So, in order to answer this question, we say the gain in pasta energy equals the loss in the water energy. Now we know that Q, heat energy, is MC, change in temperature, and you can use either delta T or delta theta for that. I'll use delta T. So we've got mass of pasta, C of pasta, specific heat capacity, change in temperature of pasta. So we've got the final temperature minus the initial temperature. Okay, because we've got a gain in temperature, we want this number to be positive. So we've got the big number minus the small number. And that equals the mass of the water times by the specific heat capacity of the water multiplied by the change in temperature of water. And again, we want this to be positive. So we're going to start off with what we know is the biggest number. Oh, sorry. Keep these as terms for now. And then take away the final temperature. Okay. So we have mass of pasta, C pasta, and so we've got the temperature we are trying to find, equilibrium temperature, minus the temperature in Kelvin. Okay, always Kelvin, please. So it's minus 10, that's 263, equals MWCW. And so it's the initial, which is 373, minus the temperature we're trying to find. And now you rearrange. I won't put in all the numbers. We can see all the numbers. I'll just highlight them here. So we've got mass of pasta. We've got specific heat of pasta, specific heat of water. So the one we're trying to find is and we've got the mass of water as well, which is 0.86, which was, oh, sorry. We've got the mass of water that is in the pan. And so when all of that is worked out, the equilibrium temperature, and you could work this through, is 359 Kelvin, or you could convert that to degrees Celsius to keep it consistent with the initial values in the question. So it's 86 degrees Celsius. Does that make sense? Yeah, it does. Okay, if I just put 86 on this number line, yeah, I'd say it makes sense. The question now moves on to electricity. We've got a voltage here. We've got a power, and they're asking for resistance. So we've got two resistors connected in parallel, and we need to link power, voltage, and resistance together. Now, power is voltage squared divided by resistance. So we can say that the resistance is V squared over power. So we've got 220 squared divided by 1.6. Be careful, it's in kilowatts. And that comes out at R equals 30.25. It's a show that, so I'm going to go to lots of sig figs. Okay. Now, question 4G is very similar. However, the key difference here is, and I didn't actually highlight this in 4F, but it's just saying switch A is closed for 4F, which meant that only this resistor was in the circuit. Resistor B, as far as it was concerned, was not taking any of the voltage or the power. So that's why I know that this answer is for one of the resistors. However, for 4G, it's almost the same calculation. However, we've got both switches. Okay, so we need to work out. Now we know that each resistor is about 30 ohms. We need to work out what the total resistance is. So if I add to the working for 4F, if I add the words the letters TOT as in total, that's the total resistance in the circuit. So if I'm trying to work out the new power transferred, I've still got the same voltage because that's the voltage that is being supplied externally. But this time, because I've got two 30 ohm resistors in parallel, they're actually going to be working together to get a different total resistance, like this. So if this is 30 and that's 30, what I would do is I would say 1 over R total, because I'm in parallel, I want to know what the total resistance is, equals 1 over 30 plus 1 over 30 equals 2 over 30. Therefore, the total resistance is 15 ohms in the circuit. So now I've got 220 squared over 15 instead of 30. And as you may have expected, depending on your current understanding, pardon the pun, of electricity, it's doubled the power transferred, which makes sense because it's going to require twice the amount of energy per